diagnose, and it turns out that you really needed flexible GMRes. So that was the equation part. So we became specific and precise in what we were doing, but so far we haven't been concrete. So let's do an example, and this is my favorite part. So right now, I want to tell you that last time I gave this, what I did is switch right now to the screen for running everything and just showed everyone on the fly, and then came back to the slides. And the problem is that, you know, that I didn't set it up as much, and I'm not sure it was as easy to follow. So what I'm going to try this time is I'm going to go through the slides first, which might be a little frustrating because I'm not running it. I wish I had two screens, right? But we don't. So I'm going to go through the slides first, maybe a little faster, and show you what's going to happen. Then I'm going to go out and actually run everything and go through it again. So bear with me here. So what I'm going to show you is the process that I really think you should go through when you start running anything, you know, tutorial example or your brand new, you know, research example. You should try to do it this way, I think. At least I think so. And I think Brad and Charles do too. So first, you try LU. Well, you can, but for any fault problem, it's going to fail. So you at least try it if you just have elastic, but it'll fail for the fault problem. And I just want to show you that failure. Since it failed, we go to the next step, which is, for us, is trying out a field split preconditioner. So inside Pilot, as I said before, every object has a name, and so the name of the field split object is starts with fs underscore. So the field split solver has this prefix, and that's how we tell it to configure itself. So in order to get the fields, we have this split fields equal true that says, you know, tell Petsy how the problem splits apart. We changed the matrix type to AIJ. This is because these kind of preconditioners break the symmetry we might have in the elastic problem, and so we need to go to the general format instead of the symmetric format. And I'll just put in this view option here so we can see what we've done. And the first thing we try out is we split the fields, but we just solved the problems independently. Now, I would never do this. I just want to show you that this does not work. Even if you solve them exactly, it does not work, and it converges really slowly. So don't do this, but do this next one, which is instead of LU, we say do the sure complement splitting, use the full factorization, and then you can see for the first problem, this problem 0, which is the problem for displacements, the elastic bulk problem, use LU. And we don't need a linear solver. We use this preconditioner only because LU is exact. And then for the problem on fault tractions, use a linear solver, GMRes, let's say, and use a very, very low tolerance. This is equivalent to an exact solver. Why don't we just use LU here, you might say? We don't because we can't. LU requires that you know the full matrix for the problem you have, but we don't know the matrix because it's given to us implicitly as B transpose A inverse B. A inverse can actually be formed because it is dense. So all we can do is act with, you have the action of A inverse. So we use one of these Krylov methods, like GMRes, that doesn't need the matrix, just the action, and then we solve it to a very low tolerance. And what you'll see is this works in one iterate. So it's the equivalent of using LU on the whole problem, is this thing. Great for checking the physics, boundary conditions, setup, everything. So I would always, always, always start with these solver options. And so this solver file 03, you can use this with TET4 or triangles or quads. It's the same. And so this, I would keep this as your baseline solver configuration. Yeah, Brad says that there's a link. They're put up. We are going to have them in the distribution for 2.0 as soon as that goes out. We're working on the last corners of parallel bugs there. I think it'll be ready very, very soon. Now, once you've got this, once you agree that your problem is good and you like the solutions and you visualized them and thought about it, then you might think about doing something that is more scalable because you want a bigger, high-fidelity version of that run. So the first thing that happened to us when we try to scale up is that the fault tractions problem takes way too long. And that's because as I said, we're solving it here with this Krylov method, GMRes, and without a preconditioner, it just doesn't work very well. It's very slow. And so what we added, and this is the major contribution of our pilot paper in JGR, is we added this custom preconditioner that allows us to scalably solve the full fault problem. And so if you add these two options, use custom constraint preconditioner, and if we tell PETSI to use our custom preconditioner rather than the bad one that it does by default, then we can take this kind of convergence, which is what you get with the full problem over there, the options in 03 that I showed. So each solve of the Schur complement takes 30 iterates here. We can reduce that to 24 iterates. Now, that doesn't sound like a huge reduction, but remember here that this 30 will grow quite quickly with the size of the problem. So I think in our paper we have examples where we go from hundreds of iterates, like 250, down to 50, so 5 times improvement, which is quite significant. And it would get worse and worse the bigger and bigger the problem got. So we're not quite to a constant number of iterates. We need to investigate the problem a little better, but I think we'll get there in the coming months or maybe year to where it's truly a multi-grid type approach where we get a constant number of iterates for the fault problem. Now, the next thing you might think of is, well, okay, so we've got a scalable number of iterates for the Schur complement problem, but we're really solving that guy to this very low tolerance, so it looks like an exact solve. What if we solved it inexactly? So if we solve it inexactly, we only took 2 iterates here, or 1 iterate here. So if we solve it inexactly, now we're going to take 2 iterates. But each iterate is much less expensive. Here we only take 10 and 10 and 15 iterates instead of the 25 over here. So overall, we save on the total number of iterates. And these are the kind of games you play with this stuff. You can try, so this was a very small change. We took, one of the tolerances and we moved it up a little. And those are very incremental, and it's very easy to see what the effect is. So those are nice. Other kinds of changes, and this was what I wanted to exhibit here, other kinds of changes are not so subtle. So for instance, we can go from our LU, our exact solve, to algebraic multigrid here. But unfortunately, when you do that, it's so inexact that you can add, so we're only taking 1 nonlinear iterate for all of these examples here. But if you make this kind of more extreme approximation, we've now gone 30 iterates. And you should remember that each of these iterates takes at least 30 subiterates. So this is a huge expansion in the amount of work. So that does not go very well. However, what you can do is you can say, well, okay, we're going to have the algebraic multigrid, but now we can't get away with no linear solver here. So we're going to add in a linear solver, but and we'll have quite a low tolerance. And with that low tolerance, we can restore this small number of iterates that we had before. So now we're not doing LU, we're doing algebraic multigrid. So remember now, LU had these huge memory requirements and time requirements. And right now we have algebraic multigrid, and yet we still have this small number of iterates in these 10 to 15, no more 30 iterates. And we've only increased the iterates that we do by 1. So what we have here at solver 7 is a pretty scalable solver that gets us the exact answer, in essence. And what we'd like is then to start fiddling with the tolerances. Well, maybe you don't need this tolerance to be 5 times 10 to the minus 10. Maybe you only need 10 to the minus 6, and maybe the outer tolerance doesn't need to be 10 to the minus 8. It can be 10 to the minus 6. And those are the kind of small adjustments and things that you can play around with very easily with this code to try and shave off the time. Once you're doing production runs of very large problems on parallel machines, these matter a lot, and so you want to play with them. But not until then, I think. So let's take a look at doing it. So right now, I'm going to go to my other machine, and I'll say stop sharing. And then I'll share my screen here, desktop. So let's see, can you see this? Yes, this worked much better. Okay, so first, everyone, we are in the examples 3D Hex8 directory. Now, Brad just sent out, this is in a slightly different place in the Windows distribution. If you're using that, I think it's under Program Files, Pilot, and Examples. Is that right, Brad?
Yeah, there's a source and pilot in there as well. But look at the email that went out, and that'll tell everyone. And it's also posted on.
Okay, great. I just want to make sure I brought that up in case people are wondering how to get here. I'd encourage you to follow along, because I'm not going to do anything sophisticated, and it's really kind of nice to run things yourself, I think, to get a feel for that. Because the point of these tutorials is, one, to provide you with some information, and that's okay, but you can get information from reading the manual or from, reading a book or a paper. But the other thing we're trying to give you in these tutorials is a mastery. We want to enable you to run Pilot capably so that you can change things and inspect things and really have this kind of sense of power when using the code, okay? And that's something it's hard to get other ways. So we'd like to show you a lot of running, and we hope you run along with us. So I always look at what's in the directory, so I've obviously got some weirdo files that I made by mistake. Yep. Probably true is also. So you can see that I have logs from old runs, and then a lot of configuration files. And so what we're going to do is we're going to run step 10, and so I did not automatically know what step 10 was, but Brad's excellent about putting descriptions at the top of these configuration files. So it tells us that this is an example which uses static fault friction. And I'm using this example because it has a fault, but the solve for the sensitivity to fault friction is not important because we're not putting enough load on it or enough displacement to initiate slip. So I'm just going to use this so we have a problem with the fault, but I'm only going to look at the main solve, not the sensitivity solve. So we can just run the thing. And so let's go over how to look at this. So here it tells us it's solving the equation. By default, we have the SNES monitor function up, so it shows the initial residual of the nonlinear equations here. And then it does a bunch of linear iterates and shows the residuals. And finally, we get down to the statement of convergence. The linear solve converged, and the nonlinear solve converged in one iterate. Now, unfortunately, we did not give the view option, so we don't see what solver we're using. So let's run it again, where we give this view option. Actually, I can just give SNES view. So you can put options in configuration files, but you can also give them on the command line, which allows you to do some of this quick and dirty stuff like I'm doing now. So let's take a look at this. Now that we've given the view option, it outputs a description right after the solve of what we were doing. So we're using Newton on the outside, which is not all that important. Let's look at our linear solve. So on the outside of the linear solve, it's GMRes, this Krylov solver, but as we know, all Krylov solvers need preconditioners. And here what we've used is additive Schwartz. What does that mean? Okay, we talked about how the field split preconditioners break stuff into subsolves. Hi, Maria. Break stuff into subsolves based on the equations. Well, another way to break stuff into subsolves is based on the domain. So you can solve the problem in a piece of the domain and then try to combine it with solves in other pieces of the domain. Now, the simplest form of this is called block Jacobi, and that's where you solve in pieces of the domain that are disjoint. Additive Schwartz method solves in pieces of the domain that overlap. So this was the default in earlier versions of Pilot before we developed our custom preconditioner, and so this does solves in pieces of the domain. On each piece, we have a separate subsolver here, and so you can see that it's named sub, and that has no solver, but it does have a preconditioner, which we use incomplete Cholesky, Cholesky is just a symmetric version of the LU factorization. And it tells us how big our problem is. We have 763 unknowns in this problem, so quite small, right? But even on this quite small problem, which is just a toy, it takes us 27 iterates, which, is a little disappointing. And I'll tell you, as you increase the problem size, these iterates increase dramatically. And that was always a problem in the early versions of Pilot. So let's take a look when we add in some solver options. So the first thing to do is say, well, let's just do it exactly and add in LU. And LU completely fails. Now, it would be great if it didn't completely fail, if it just said there was an error. But the problem is that our description is so incomplete that Betsy fails outright. And let's look, what were we? We were just trying to use LU. So instead of that, let's just go straight to solver 3, which is the full sure complement version. So this is great. So let's look at it. Here we can see we took one linear iterate and only one nonlinear iterate because it converged after that. And so perfect, right? It's just like LU would be. And we can see that there's subsolves here of 30 iterates and 30 iterates, which are the solves for the sure complement. Now, let's just make sure we have what we think we have. We have GMRes on the outside, but instead of additive Schwartz, we now have this field split preconditioner. It tells us that we've used the sure complement form instead of additive or multiplicative, and a full factorization. And then it says these splits were defined by Pilot. It passed in this construct, this IS construct. So let's look at the individual solvers. For the displacement, the name is now, see, I'm running the 2.0 version, so the name, instead of being FS field split 0, is FS field split displacement, which is a little more specific. And here we're just solving it exactly with LU, and there's a bunch of options for that. And you can see that the problem size for the bulk elastic part is 658 out of 763. And then for the part on the for the fault tractions, we have the Schur complement operator. A11 is a 0, so this is just B transpose A inverse B. And this has a name, FS field split Lagrange multipliers, or you might say fault tractions, whichever name you prefer. And this is solved by a subsolver, as I said, the GMRes, and then this Jacobi preconditioner is just diagonal preconditioning. And inside, it tells us how we are dealing with the Schur complement. So it tells us, for instance, that this A11 is actually a 0 matrix. This A10 has 105 rows with 658 columns, so it transforms from the bulk elastic problem to the fault problem. And here we have this A00 inside of this operator, this inverse A00, it describes the subsolver here. Now, if you don't tell it to do anything different, it just keeps using what it used above, so this LU. But you could, for instance, use LU for the problem up here, the main bulk problem, but within the Schur complement itself, you can use a different solver, say multigrid. So there's a lot of options for customizing the solver, and they all have slightly different effects. So there's a lot of room for experimentation. So let's see, the solver 3, as we said, it just introduces the field splitting and changes the preconditioner type to field split with a Schur complement formulation and a full. An LU for the displacement subproblem, and then a very low tolerance for the Lagrange multiplier problem. And you can see here I've given KSP converged reason. Since I gave that, it told us how many iterates were used for each of those Schur complement solves. You can give this option for the displacements if you think the displacements is slow, or you could give it for the full. We have also given it for the nonlinear problem, so it tells us when it converged. So you can get a lot of information out flexibly. Now let's look at improving this. When we improve it, one way we could go is to use an effective preconditioner for the Schur complement. And so we're going to use our custom constraint preconditioner. And with that, you can see that instead of 30 and 30, Instead of 30 and 30, we take 24 and 25 iterations. And as I said, if you increase the size of this problem, they diverge dramatically. And you can see the numbers in the paper. And if we go down here, what we can look at the Schur complement. Well, the field split preconditioner first tells us that the preconditioner for the Schur complement is formed from a user-provided matrix. Whereas if you look at our last solve, the preconditioner for the Schur complement was formed from A11. Now recall that A11 is 0. So it didn't give us any information, and that's why the preconditioner was so horrible. And so now we've given it an actually good preconditioner. And let's see if I can get any more information about this. Oh, I could just get the size of it, but it doesn't tell me any more information about the custom preconditioner that we've given. Now, we can imagine, as I said, weakening the Schur complement solve. So it will solve faster, but the convergence of the whole problem will be weakened. So instead of our exact solve, where we get the right answer in one iterate, now it takes 2 iterates. But you can see that each iterate is a more efficient solve. So here we take 35 iterates overall instead of 49 that we took before, right? So an overall win. And these are the kind of games you play. I said you can make more drastic simplifications. You can, for instance, change LU to this algebraic multigrid, but that can be pretty disastrous. because what happens here is these sure complement iterates are converging. So why, if they're converging and they're converging to this low tolerance, why is this norm all so far off? And the reason is the very definition of our problem relies on that A inverse inside the sure complement being exactly A. And since it's not, since it's very far from being A inverse, then the definition of our problem has changed, and this is what causes this large number of iterates. And so I can kill this here, and we can fix this up by introducing a solver where we only had the preconditioner only before, and we can restore this small number of iterates. So what you see is it took a little longer. This is actually takes longer than the LU version because the problem is so tiny. But the amount of work for the algebraic multigrid scales linearly, whereas the amount of work for the LU version scales like the cube. So very, very rapidly, this becomes a lot more efficient than the LU version. And so this is the real baseline for efficient solves in Pilot. Now, depending on your problem, you probably want to mess with the tolerances. You probably want to mess with exactly what kind of solver you're using. There are options for GMRes, for instance. How many restart vectors do you want to keep? What kind of maximum iterations do you want to allow? What kind of tolerances do you want to use for the problem that you're doing? And so all these come into play. But the structure of this particular solver is scalable, and it's fairly efficient right now. And so this, I think, is a good starting point, this solver 7. And in fact, we're having these discussions today about the Green's function runs that Charles is doing. And this is how we proceed. So let's see, I think that's all of the stuff I was going to say about linear problems. Does anyone have a specific linear question before I talk? I was going to talk a little bit about nonlinear problems after this, but only in the context of PETSI because we haven't quite moved that nonlinear expertise over to Pilot yet. We're getting there, and that's why I want to just introduce it this time. I didn't talk about any of it last year, but this year I'm going to put a little bit in, but it's not quite where we want to be. So does anyone have anything that wasn't clear or anything that they don't understand about these solver configuration files? Okay, if not, I'm going to go back to sharing, which one?